Good afternoon, Professor.
Good afternoon, Caroline. Well done. Good afternoon. Oh, good afternoon, Amanda. Oh, wait. Good afternoon, Amanda. Good afternoon, Kevin. Good afternoon, Adon. Good afternoon, Caitlin. Wait. Good afternoon, Samaya. Good afternoon, iPhone. Wait, I think I know who that is. iPhone is Samuel? No. I can't remember who iPhone is, but hopefully it's Stephen. Wait, Stephen. Which Stephen? Stephen. Stephen. Right. Sorry. Yes, of course. Thank you.
Good afternoon, Professor.
Good afternoon, Savannah. Good afternoon. And good afternoon, Stephen. Sorry about that. Good afternoon. Okay. Excellent. Okay. Okay. All right, let's get started. Did I say yes? Hello, everybody. Okay. Oh, good afternoon, Jose. Oh, and here comes Jose. Okay. Okay. Oh, and of course. Okay. Anyway, all right. All right, so here's the deal. You might have noticed that various announcements and pieces of information about an upcoming midterm have been posted. So we do have to have a midterm exam. Well, let's start with this. Did everybody see that in their Google Classroom was a practice exam posted for this midterm? Is it okay? Thank you, Caroline. Okay, awesome. I'll take that as all right. Well, Caroline's got it. So Caroline said, no, everybody. Okay. Tell me if not, but okay. Thank you, Amanda. All right. Awesome. So that was posted before I even established an actual date for so the bottom line is this. Originally, I was going to have the midterm be posted tomorrow, like this coming Thursday, and then have it be due next Monday. But then I missed a class and we didn't talk about it, stuff like that. So to be utterly blunt, I don't like midterms any more than you do, I may like them slightly more than you do, but I don't look forward to them any more than you do. But we do have to have one. We try to make it a real experience, but a real intense experience rather than a real stressful experience. I mean, some of you who already know me know this is what we try to do. It's not going to be easy, but hopefully it won't be full of surprises or games or hide the ball or anything like that. Where I'm going with this is this. It seems like the best time to have it so that it's not too close to the final exam or anything, or it doesn't conflict with your vacation or doesn't ruin your vacation or conflict with religious observances. As I think it says in Google, what we're going to do for this exam. So we're going to spend a lot of today talking about this exam, okay? And today won't necessarily be the only day we talk about it, but we're going to spend a lot of today talking about this exam. So please bear with me. Number one, the exam will be posted at, thank you. Yeah. Oh, you too. Thank you. Yes, it is. Thank you. You too. So the exam will be posted a week from today, Wednesday evening by 8:00 p.m. That's when it'll be posted. It'll be due back to me the following Monday, right in time for class. That Monday is your last Monday before vacation. I mean, I think you go away on vacation or on holiday that Wednesday, right? So the exam again, it says it in Google Classroom. The first thing I want to do is make sure this is clear. I believe it says in Google Classroom that the exam will be posted a week from today. That would be March 29th. And then it'll be due back Monday before class starts. That would be Monday, the April 3rd. And yes, wait, so yes, direct chat person. Yeah, that's what I'm about to, yes. Okay, and I'll even answer that question in a second. But sorry, if you, okay, cool. Okay, yes, cool. But again, just clarify with me, just like look at Google, make sure we're both on the same page, you and I, all of you and I. I'm saying the exam gets posted a week from today, and then it's due back to me right before class, Monday, is that the 4th, the 3rd, Monday the 3rd, whatever, I'll look at the calendar, whatever it says, but Monday, right before spring break is when it's due back. Can someone just confirm that can you confirm that that's your understanding, that that's what it says in Google Classroom and that you're understanding? Thank you, Caitlin. Okay, that's good enough. Thank you, Caroline. And thank you, Katya. And thank you, Savannah. Okay. Okay, so so now let me explain. So if that's clear, let me back up for a second and say some things. If you've ever had me as a professor before, like in Physics 203, then what I'm about to say is hopefully old news to you. Like, yes, it's going to work like it did in Physics 203. And yes, we're going to try to prepare for it, much like we did in Physics 203. But there's a question in the direct chat. There's a couple of questions in the direct chat already. And to those of you who don't know me, let me make this very clear. It is an untimed exam. There is no timer for the exam, if that's what that question means. Like, the timer is just that you have to turn it in by class time, Monday, April 3rd, or whatever that, Monday, April, Monday, so I don't keep stuttering over this. It's Monday, April 3rd. Yeah. So the only timer on it is you have to turn it in by 3:05 p.m. Monday, April 3rd. And that's it. You could take as long as you want on it. Also, let me make it clear to people that don't know me. It is open book exam. You can use all your notes. You can look at YouTube videos, my YouTube videos or other people's YouTube videos. You can use a textbook if you have one. You can walk away from the exam and then walk back to it. You also can and should talk to your friends. You're allowed to do anything you want to take this exam. It is open, everything exam, and there's no timer on it. In fact, person in direct chat who just asked me, is there a timer? Could you just confirm in direct chat that you hear and understand my answer, or that I'm answering your question? Like, it's totally untimed, totally open resources. Could you tell me if that? Okay, great. Thank you. Okay. So that's unusual, right? Well, maybe it's not unusual if you're getting used to it in Physics 203, but it is what it is. Now, like it sort of says in Google Classroom, and like I'm going to try to remind you in more ways than one, the exam is going to be very, very similar to the practice exam. There will be some differences, but it'll be same basic content, same structure, same format. I'm just going to change some details in some of the parts of the questions. And where I change details, it might make an important difference. Like I will change some details so that you have to think and you can't just copy your answers from the practice exam. But the practice exam is there to give you a sense of how long it would take you to do this and what types of thing you have to do and all that kind of stuff. And yes, someone asked in the direct chat, yes, we're going to spend today talking about that practice exam. We are. And there's videos posted about parts that we don't get to. I mean, I'll be clear about all that. But what I want to say to all of you is I'm going to try to address many of the aspects of the practice exam. I'm going to try to point out what to do here or what to do there. I won't get to all of it. I'll get to as much as we can. Some of what I don't get to here, I'll tell you where I did it in a different section and posted the video for you. Okay, I'll make that clear as we go through. In a minute, that's what we're going to do. In a minute or so, we're going to walk through the practice exam, and I'm going to just give you hints or advice or answers or different things as we walk through. And you can stop me and ask questions. But basically, we're going to do like a walkthrough of it, so at least we know what to expect and stuff like that. And I'm going to tell you right now that anywhere that I give you an exact answer, or if I give you an exact solution, or if I post a video that has an exact solution to something, then that's great. And you can use that. You should use that to learn, but you can also assume that I'll change the question somewhat to make sure you don't just literally copy that solution. But anywhere that I don't tell you exactly what to do, anywhere that I say, okay, in this, I think you could figure out, or this, you'll use this equation, but you'll figure it out or something, then you could or if I just skip a question entirely when we're walking through it, you can assume that you'll have that exact question on your actual exam. So basically anywhere on your actual exam, you either will be have a little practice with me of what to do in advance, or you'll at least have the advanced warning of knowing that's what the question is. And let me say again, you are allowed to work with one another. You're not just allowed, you're encouraged to work with one another to get the understanding. You're allowed to go to Khan Academy to get on the web, to get the understanding. The goal of this exam, and you're allowed to admit to yourself or to me or to someone right before you start the exam that you still don't understand. This exam is not to find out who did understand what when. This exam is to get everybody to understand. It's an opportunity to get you to understand so you can do up until the very last minute. And I know some of you have heard this speech before, but up until the very last minute that thing is due, you could still be holding each other's hands and explaining things to each other. As far as I'm concerned, you could do whatever to get one another to understand this material. But then you've got to know, this is the important thing to everybody who's asking questions. Then when you sit down to write your final copy of the solutions to this exam, and when you sit down, it should be a final copy, like blank sheets of paper where you go through the 5-step method for every problem, where you give a diagram, where you make it clear what the question is, where you act like your blank pieces of paper are a blue book, right? You don't copy and paste my questions, you don't insert my questions, but you make the questions so clear that I can read your material without having to look at the original questions, right? And you make it so well presented that it's probably the result of a rough draft or rough drafts that you did first, and then finally got all your answers together, figured out all your answers with your friends, and then you sit down to make a final copy and walk me through all your solutions on your final copy. The key thing that I cannot emphasize enough to everybody is you have to know that I know that you know that you have the answers at your disposal. We both know that you've got the World Wide Web and all your friends and my videos and everything to tell you a lot of these answers in advance. Therefore, it is not good enough for you just to give me answers. Like, that's not the point of the exam. The point of the exam is not just for you to spit back answers to me. I already have them. The point of the exam is for you to show me the thought process that leads to those answers, and show me that by the time you've sat down to write out your final copy, that you understand the material. Therefore, a lot of things, so therefore do more than one copy. Give yourself time to do rough copies. And when you sit down to make a final copy, your goal is to give me a document that I can read from beginning to end without looking at anything else, or really that anybody who knows physics could read from beginning to end. And I don't have to be looking at the original exam sheets. Somebody else doesn't have to be looking at the original exam sheets or be in the class. They could just read it from beginning to end, and every single problem, every single solution that you've written down makes it totally clear. Here's the problem, here's the situation, here's my thought process, here's the intricacies of the problem, here's the final answer to the problem circled. Like, you should produce a document that is self-contained, self-supporting, physics proofs, And what are you proving? You're proving the answers to these problems, and you're proving that you really understand them. A lot of things that would normally be considered cheating are not considered cheating in this exam. Like talking to another person is not considered cheating. Opening up your book or going on the web while you're even doing it is not considered cheating. But you got to remember that I know that you're going to do that, or I hope you're going to do all that. So what is cheating in the end, the one and only thing that's cheating, is writing down things that are true, but that you don't understand. And honestly, I can spot that much more easily than many of you think. I know the difference, and the way I spot the difference and what you're trying to show me is that at the end of the day, you get this material your way. You are going to make it as personal and as graphic and as clear and as thorough as possible. Like you're going to make it look like some of you have amazing class notes where you use different colors and you draw little pictures and you make comments in the margin about what's going on. That's what you want your exam to look like. Many colors, notes in the margin, pictures. You're walking me through your mental process to show me what you now understand. If you write down things that you don't understand, even if they're true, it doesn't matter. You don't get credit for them. You have to show me that you understand them. And believe me, I know the difference. It's the one thing I do know in this world. I'm going to stop babbling and yelling in a second. I'm going to go back to logistics, but just to make it clear, your job is to give me a well-presented document of physics. Use the document as an opportunity to explain the physics to me. When in doubt, at any moment when you're writing this out, any moment your brain goes, wait, so I just divided both sides by 2. Does he really want me to like show the step I divided both sides by 2? The answer is yes. Anything that ever occurs to your mind as a possible step that you might possibly want to show me, show me. If no step is too small, the more small steps you can show, the better. Because the more small steps you show, the more it's going to end up actually being your personal work and not just a standard regurgitation. And again, that's what I'm looking for. I'm looking to see that you personally have filtered all this through your perspective and it's come out on the other side. Okay. I will answer. Is there more in the chat? Okay. So that's what's going to be due Monday before class, Monday the 3rd of April. I'm going to start walking through the practice to show you what I mean in a minute. But again, whatever you've done on homework is the practice for this. That same method, same type of thinking. Definitely do this on separate sheets of paper. Definitely don't do it on the exam sheets. The other thing about, again, we're going to start walking through it in a second, but as far as the timing is concerned, I keep saying, and it's true, it's due right before class on Monday. Part of the exam experience is coming to class. I've mentioned this last semester too. Your job of taking this exam ends once class ends that day. You turn in the exam before you show up to class, and then you come to class, to Zoom class. You come to class and you make an appearance and you show your colleagues that you're here and that you've turned in your exam. And I'm serious about that. Otherwise, if you're not here, your colleagues think that you're still working on the exam in the last hour while they already cut off their work and submitted the exam to me and they're here. And if you're not here, whoever you are, they think that person just got an extra hour on the exam. Why is that fair? And Yavrabam's such a pushover, he's probably not going to penalize them for it. And I'm here to say, yes, I am. Like the one thing that is serious is exams. Homework, you can still be turning in homework 1, as far as I'm concerned. That's fine. You can still be turning in homework 2 and 3. Totally fine. I'm telling you all that. But the exam is different. You got to turn the exam on time, and then you got to show up to class to show your classmates that you didn't cut a corner that they held back from cutting. I've said this before too, but I'm a very strong believer in this. You're good, especially if you haven't had me before, you're going to think that I'm letting you do a lot of things on this exam that you might consider cheating. I mean, in other classes, they are considered cheating. I could talk to you for a million years why I believe in doing it this way, and why it's still possible for people to get very bad grades on this exam if they don't take it seriously. But hopefully it's more possible for more people to get good grades. The one thing is what I actually believe is cheating is when one person gets away with something and gets an advantage that all the people that are trying to do the right thing didn't get. Cheating is like taking advantage of our capacity to do a weak or unethical, to break the rules. Cheating is when one person takes it upon themselves to think that they're above the rules, and then everybody else followed the rules and they do worse because they followed the rules. That's totally unfair. That I don't believe in. So that's why I'm saying you all can use the internet. You all can talk to one another. I hope you do all help one another. I want it to be an even playing field. So then the one thing that would be uneven is if one of you just took an extra hour and a half. Anyway, you get my point. Show up to class turn in the exam, then show up to class that day. And now, last thing about all that, that's what I'm saying is the system for everybody. I did poll the other class for input onto exactly when to do this exam. I tried to do it under these circumstances. I tried to make it conflict as little as possible with quant and with orgo. I understand this is a rough time of year for everybody. I think this is the best overall time to do it, but I will tell you, having said all this, if you have a personal issue, I guess I put this in Google Classroom, but if you have a personal issue, like you happen to be the only one who's in a certain quant section or something, whatever. If you have an issue and you already know that you're going to have a trouble getting this exam in on time, you can and should reach out to me personally, like not right now, not in the middle of class. But if you text or email me in the next couple of days and you say, I already know I'm going to have an issue with this exam, with the timing, then you and I, whoever you are, will work something out personally. And I'm telling you that, I'm telling it to you all. Again, I don't think it's an unfair advantage. If someone comes to me in advance and says, can we work something out? I will probably help that person. And that person may or might not be you, but on the final exam, it might be you, right? I'm just saying, if you think, but you have to tell me in advance and we have to make an arrangement and then we have to stick to that arrangement. If you just turn in the exam late without any warning, or if that morning of the day that it's due, if you suddenly text me and say, I need more time, that's a little dicey. No, if you know in advance you've got a situation, we can work with it individually. And I'm saying that to all of you. So even though it probably would only be a couple of you, it could be any of you, if that makes sense. Okay. All right. But that's just again to say, if you already know this is coming at a crazy time and you weren't expecting, just talk to me personally and we'll figure something out. All right. So one person asked in the chat, are we going to go over the practice midterm? Yeah, I want to start addressing the practice midterm. I do, like basically right now. But first, let me can you put a show of electronic hands if is all this clear so far? Do you understand? Okay, cool. Thank you, Erica. Thank you, Caitlin, Caroline, Caitlin, Estrella. Thank you. Awesome. Stephen, thank you. Okay, Mackenzie, thank you. Okay, Rashman, thank you. Also, one more time, I'm going to put in the chat my information. Oh, and if that's a question, thank you, Jose. So in the chat, just in case. And I do know that there's a quad thing due anyway. But that's my emails. That's the best email to use if you have an issue. The earlier you tell me, the more we'll be able to work together. And then also. Okay. Now let's. Right. So today we're going to talk about the exam. I mean, we're going to walk through the practice exam. I'll probably do a little bit more of this also on Monday. I probably won't. Then I'll probably stop and move to new material Wednesday. But again, to be clear, even if we start going on to new material or something Wednesday, like what's on this exam is what's in the practice exam. Your exam will definitely not be longer than the practice exam. It won't have any problems in it that aren't in the practice exam. Your exam will be modeled on the practice exam and maybe shorter, like somewhere in it, I might give you choices. Maybe we'll talk about that in a second, but it won't be anything that's not in the practice. So just know the whole practice and you'll be set. But okay. Okay. Yeah. Okay. So I'm going to switch screens now. I'm going to switch screens. How do I do that again? Okay. 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 Just think for a second. Yeah. Okay. Okay. So, so this is a practice. This is the practice exam right here. You can see this on your screen, right? Notice it says updated Tuesday. I mean, obviously this is an old exam, but that's fine. If I publish an update to your practice exam, that means I found errors or something like that. Any new update that I publish just makes it, or that I post makes it that much more similar to your actual exam. Like the whole idea behind all of this is that the physics is hard enough. I think the physics is hard enough. When in doubt, assume I'm not trying to trick you. I'm not trying to surprise you or something on the actual thing. So if I find an error in this or something, I'll post an update and that will just make it more similar to the actual thing. Okay. Now these equations are given, right? You don't necessarily use all these equations. In fact, I can tell you, for example, equation 13, you're not going to use on your exam. I mean, it's not there to confuse you. It's just something we know. You're probably not going to use 13 or 14 on your exam, but that's fine. You don't have to use all of them, but any of them you can use. But, again, you're allowed to go on the internet and all that. So why am I even bothering giving you equations? Partly, I'm bothering to give you equations to give you a sense of what I mean by a step 3 GDP. Remember, step 3 is general definitions or principles, and you've got to do that in every one of your solutions. I really recommend you, I insist that you do the 5-step problem-solving method to do your solutions. So 2 things on that. One, you'll notice I posted another summary or one sheet explanation of the 5-step method. It was done by one of you last semester. Like it was done by a student last, but I think it's good and clear and direct and walks through an example of using the 5 steps. So you have 2 in the Google Classroom. You have 2 sheets that summarize the 5-step method. You got to use it. That's what I'm looking for in this exam. I'll show you examples again in a minute, I'll talk, but remember, step 1 is diagram or fact pattern, a diagram and fact pattern, whether or not the problem provides you with a diagram. You got to start with a diagram. Step 2 is what is the question? You've got to make the question clear. Again, you want to give me a document that would make sense to a physicist, even if they're not in this class. And that's practice for publication and research and all that. And or you got to give me a document that I can grade easily and clearly without having to go back and forth between documents. It's to your benefit to do that. So step 2 is what is the question? You got to make the question clear in your words. You want to show me that you know what the question is. But then step 3, GDP is general definitions or principles. I can't emphasize this enough. That is not the same thing as writing down the facts of the question. The facts of the question are in step 1. Step 3 is truths about the universe that are true even before we look at the question. That's a very important distinction. Step 3 is often triple equal signs, not always, but often triple equal signs. So step 3 are about places that we can start our analysis, fundamental truths that from which we derive things, not truths that have been derived from other things, right? So step 3 is supposed to be things like F net equals MA. We don't derive F net equals MA from anything. We derive things from it, right? So part of the purpose of this equation sheet is to give you an example of what I mean by a GDP. Like these kinds of things would be the kinds of things you would put down in step 3 GDP. So notice again that if you do this 5-step method correctly, you have 3 things to do before you even start working through a problem. There's always stuff to do, even when you think you don't know what to do. There's 3 steps before you even start doing any kind of computation. Anyway, so these are equations that are examples that you can use in the exam. But if you find an equation that's not one of these and you find it on the internet, I would be very careful. Like I might have left some things off here, and there are things that are true, that are reasonable, but anything you find on the internet, don't just quote it just because it's on the internet. Like you've got to explain. Like you want to err on the side of things that actually happened in the class. Anything that I notice especially if I notice a Greek character or something that we've never used before. That's definitely an alarm bell to me. And if I ever write well, anyway, you get my point. So be very careful of things that didn't come directly from this class material. The 5-step method is also the way I grade, right? Like the way I know what I'm looking for. This is what I was going to say. What I'm looking for is the steps. That's how I grade. And if you're missing steps, that's where I take points off. Not necessarily if your answer is wrong or whatever. And you don't get all the points just because your answer is there. I'm looking for the steps. So that also, to answer a question that people ask me a lot. So am I saying that you literally should write step 1, step 2, step 3 in your solutions? Well, I can't technically take off points if you don't, because that's not technically like physics. But I would say this, it would be very wise for you to do that. There's no harm in labeling step 1, step 2 as you go. And the more you do it, the more you're just ensuring to yourself that you're checking off a grading rubric while you go. Like it's there for your benefit. If you actually write step 1, step 2, step 3, I think that's highly advisable, and it will certainly make it that much easier and clearer for me to follow your work. And that's your goal. So, okay, so I would really follow the step method rigidly. And if I ever, and that's what the acronyms are for. If you get back your exam and I take off 2 points and it says WIQ, you know what that means. I'm saying, where's the question? One acronym that's not part of the steps, just to alert you, if I ever write WWW, which stands for what, why, where from, okay, that's a shorthand for saying a lot more explanation is needed for this equation that you wrote down. Like, this does not stand on its own 2 feet. It's not a GDP. It's some kind of derived thing that requires a lot more explanation. And probably what I'm subtly saying is, I don't think you understand this. I think you got this from the internet and you're just like writing it down, and you don't want to do that. Okay, anyway, you get my point. Anyway, okay, so that's about the equations. All right, so then it says instructions for this practice, do all problems. That's for the practice. You should do all the problems for the practice so that you can, but very possible on your test, it'll say, very possible it'll say, definitely do problem 1, definitely do problem 3, and choose problem 2 or 4 or something. Whatever it says, do it. Don't, if it gives you a choice, don't do both of the problems and then expect me just to count the better one. Or give you extra credit. I won't do that. That's going to make my life harder. I need to know what you know. So if it says choose a problem, choose a problem. Okay, so now we get to the first problem here, a heat harmonic hypothesized. Again, this is a walkthrough. Okay, you notice I'm staying on this board. I'm not writing things down on the screen. So I'm giving you like an overview of this whole thing, so there's no surprises. So I'm just talking. If I would highly suggest that you take notes of what I'm saying now, but it may be a little abstract because I'm not writing things down myself. So stop me in the chat if I'm going too fast or too garbled. Okay, because any of you who's paying attention now is obviously going to have a much easier time with this test than anybody who's not paying attention right now. So on this first problem, this is homework 3 in effect, right? This is homework 3. And even if you still haven't done it, that's fine. But this is homework 3. The main insight of this problem, the main thing that drives the whole thing. Well, you're given this differential equation that supposedly describes temperature. You might think, we've never discussed temperature before. How is temperature suddenly part of this class? The whole point is we've been discussing harmonic oscillation. What we've been trying to say is that any system that obeys the basic math of harmonic oscillation obeys all the math and all the physics of harmonic oscillation. And the basic math and the basic physics came from a mass going back and forth on a spring. So the ultimate physics lesson here is that anything that is described, any system that's described by the same differential equation as a mass on a spring will behave just like a mass on a spring. So this temperature system here, it's described by that differential equation. Here, temperature is designated with D. It says the second time derivative of D is directly proportional to D. Well, is directly proportional to the negative of D. The second time derivative of D equals negative times a constant times D. That is the differential equation for harmonic oscillation. That means D, the temperature, is oscillating harmonically. The value of D is going up and down in the manner of a cosine function. Sorry, I'm talking too much. The insight is, if I see that differential, so I'll give you the insight and I'll tell you how to say it in step 3. The insight is, if I see that equation, what I should automatically be able to recognize at this point is that D is oscillating harmonically with an angular frequency of 25 radians per second. Like, the insight of this problem, the main thing to know, now you have to explain it better. That I just said it. I didn't explain it. You're gonna have to explain it. But what I'm saying is, if D is described by that differential equation, then the solution, or a solution to that differential equation, is D equals D naught cosine 25 T. Where did I get 25 from? It's the square root of 625. What I'm saying is, at this point, the conclusion that we want to realize about harmonic oscillation is, or let me say this. What I would write for step 3 for GDP, what I would write for a problem like this, I would write something like, so this is step 3 GDP. Like, I think you can do, well, step 1, I would make a cosine graph. Step 1, I would make a cosine graph, and I'd make the cosine, this axis would be T for time, this axis would be D for temperature, and I'd have a cosine graph that starts on the D axis at a value of 150, right? Because it says at D naught, like, the initial temperature is D naught equals 150. So I would make a cosine graph for the initial temperature is 150. And then the cosine graph will go back and forth and back and forth. So you have time measured in seconds, temperature over here, and a cosine graph starting at 150 going back and forth. That would be my diagram. Then what's the question? You can see what the question is, how much time will elapse. But my step 3 GDP would be something like this. I would say for step 3 GDP, I would say something like, in general, for any general variable Z, if D2Z over D squared equals negative 625 Z, then the value of Z oscillates harmonically according to the expression Z equals Z naught cosine omega T. I'll say that again. And I'm not saying you have to say my exact words. In fact, the more you don't say my exact words, the better. What I'm saying, though, I will say it again in a second. I'm saying a GDP is supposed to be some truth that's going to help us with this problem. Not a truth that comes from the facts of this problem, but a truth that was true before the problem and helps us. So a general truth here is that if you have any variable at all, Z, right? So I'm intentionally changing the Z now so I can make a general point. If we have a differential equation in Z of the form D2Z over DT squared equals negative omega squared Z, right? And I hope that's what I said 2 minutes ago. But if I have an equation of the form D2Z over DT squared equals negative omega squared Z, then a solution to that differential equation is Z equals Z naught cosine omega T. Like, you would explain that to me in step 3. Now, if you don't get what I'm saying, if you just heard the words and wrote them down, but you don't get them, then I'm telling you right now, fine, that's fine. But now you have to study and talk to your friends. And like, now you've got something to figure out here. Because if you just heard the word, I'm not criticizing anybody, but just to give you a litmus test of how to do this test, if you just heard my words and you wrote them down, but they don't like mean much to you, but like, you know, they're like the right answer because I just said them. I'm telling you right now, if you just literally try to just write those words on a piece of paper and hand it to me, by the time it got to me, it wouldn't translate right. Like I would know. I mean, you wouldn't be able to translate because it's too complicated. And if you need me to repeat that like 6 times for you to get it, I'm not criticizing you, but I'm saying if you need me to repeat that like 6 times for you to get it exactly right, then you're trying too hard to get it exactly right. What you want to get. So write something down and talk to your friends or go on YouTube or whatever. And I'm not saying that critically. There's still time to study and learn and figure this out. But I am saying what you want to be is at the place where what I just said, just you were like, oh yeah, I know what he's talking. Yeah, that's that thing where you do the square root of the thing. Like, and if you're like, oh yeah, I don't have to write down the exact, or you're not having a hard time writing down it just because you basically know the idea and you know what I'm talking. Good. Then you're going to expand on that when you take your exam. The thing that you're going to expand on, for example, is when I say d2z over dt squared equals negative omega squared z, I'm saying omega squared is just supposed to stand for any constant numerical value that's coming right before the variable. Those of you, and again, I'm not saying this to criticize anybody, but so that you can like know whether you are in the right place or not. I'm saying there's some of you in the room, when I go omega squared, you know at this point, oh, he just means the constant, like 625. But some of you might still be saying in your mind something I said for years, which is, wait, why does he keep saying omega squared? If it's just a number, why does he keep squaring it? Like why is he called omega squared if it's just a number? And the reason it's fine if you're still wondering about that. And it's fine, but you want to get it straightened out. You might even write in your exam, like, let me straighten out first. Why I keep calling that number omega squared is because I'm trying to emphasize, number one, that it's definitely a positive number, but number two, that it turns out that the cosine solution to the differential, like that stands for just any number, any constant of proportionality. But it turns out to solve that differential equation, we're going to get a cosine function where the angular frequency, what we call omega, will always turn out to be the square root of whatever that number is. So we call that number omega squared. What I'm ultimately trying to say, and I will move on in a second, I promise, but I think like this whole problem pivots, the whole point of this problem is for you to show that, you know, when you see that differential equation, you can show that the solution is of the form z equals z naught cosine omega t, where omega is the square root of whatever that constant is in the differential equation. Now, I'm still in step 3 here and what I'm talking about. I'm still in step 3. You can show what I just said. You could show that you understand it. You could show that it makes sense by saying in step 3, for example, take 2 derivatives. You could take the first derivative of z equals z naught cosine omega t, and you'll get the derivative is negative omega z naught sine omega t. Then you could take another derivative and get that the second derivative is negative omega squared z naught cosine omega t. And then you can circle that part where it says z naught cosine omega t and say that's z right there. So you can say, you see, if we say that z is equal to z naught cosine omega t, and if we take 2 derivatives of that, we do get back negative omega squared z, right? This would all be like step 3 stuff. And this is the first problem on the exam. So it would be good to go a little bit to town and show me all these steps and show me where that cosine solution differentiated twice does give you this differential equation, right? Now, again, some of you know exactly what I'm saying right now. And I don't know who you, whatever. Some of you know exactly what I'm saying right now, and I'm saying too much. And some of you are like, wait, what the heck is he? Take it. If you know what I'm talking about right now, take this as advice about how to do your exam. Like, go crazy with the more you get what I'm saying, the more you should say to take it as an opportunity to grandstand your own comprehension. If you don't know what I'm saying right now, please take this as advice of this is what you need to get before, and you need to get it solid. Don't think that because you're going to have the practice exam in front of you when you're sitting down to do this, or don't think that because you have the videotape in front of you, that'll be good enough. It won't be. Like, you got to get how this makes sense. Once it makes sense to you, once it seems clear to you and obvious, then you could sit down and write it. All right, so that was step 3. Step 4, we would then say, okay, here in this case, instead of Z, we have D, which stands for temperature. Okay, in this case, we have D instead of Z, standing for temperature. And in this case, omega squared is 625, right? In this case, omega squared is 625. Oh, and in this case, D naught, the initial value of D, is 150. So in this case, we have D equals 150 times cosine of 25t in this case. Omega in this case is 25 radians per second. Now, I'm still in question 1 here. I will go faster momentarily, but I'm just trying to, again, show you like how you do this. So in step 4, you're saying all this. So now you have omega equals 25 radians per second. Now, what it's asking for is period. Well, it's asking for the time that will elapse before the very next time that the temperature returns to 150. It's asking for the time for a full cycle. So now you can say something, and I apologize, you could say something now that really also should be in step 3 GDP, something that should also go in step 3. So I apologize, you can put this back. Something that should also go in step 3 GDP is something like omega equals 2 pi over capital T. Or even better, you could walk me through. Period of time means number of seconds for one cycle. The number of seconds for one cycle, by definition, is the reciprocal, is the inverse of the number of cycles per 1 second. Like T is equal to 1 over F, where F stands for standard frequency, number of cycles per second, right? And by definition, there are 2 pi radians in every 1 cycle. Also, definitely a GDP that I would write down. There's 2 pi radians in every cycle. I think we went over this yesterday, actually, but therefore, if angular frequency means number of radians per cycle, we could take the angular frequency omega, therefore standard frequency F equals angular frequency omega divided by 2 pi, right? Because there's 2 pi radians in every cycle. So if you know the number of radians per second, then you divide by 2 pi and you get the number of cycles per second. I'm pretty sure we just did this on the board on Monday, I hope. So then you have F, and if you flip F, once you've gotten the number of cycles per second, if you flip that, you have the number of seconds per cycle, and that will be the answer to number 1 here. Okay, now that's a lot of talking. Again, so if nothing else, take what I'm saying as this is what you have to look up or talk about with each other to figure out to write for number 1, but that's how you do it. You'll get that omega equals 25 radians per second, and then it's your job to figure out if it's 25 radians per second, then basically it's about 4 cycles per second, right? Because there's about 6 radians in every cycle, right? So if it's 25 radians per second, it's about 4 cycles per every second, and that means it's about 1/4 seconds in every cycle. So the answer to number 1 is something around 1/4 second. That's how you do it. And you circle your final answer. Obviously, I'm not going to walk this much detail in every single one, but that's the heart of this problem, was doing all that. I'm going to pause for a second for questions. But one last thing also. One correction, one mistake in this problem that I apologize. All the temperature values are given in Kelvin. That's actually a mistake. They should be Celsius. It won't change the way you do the math, or it won't change anything I just said. But I will change it for the actual exam, and for your sake, you should change these Kelvin things to Celsius. The reason being that your answer should fluctuate around 0. You should get positive and negative temperatures if it's a oscillation, but Kelvin doesn't allow for that. So they should be Celsius. Now I'm going to pause for a second. I know that was a lot of talking and I didn't write anything down, which is sort of unfortunate. Can you just raise your hand if you more or less followed the skeleton of what I just said for number one? Great. All right. Awesome. Awesome. Thank you. Awesome. Okay. Okay. Now I'm going to tell you so far, everything I'm doing here, I'm looking at the time. We got 25 minutes left. Okay. I'm just continuing to walk through here. I'm also going to encourage you that I did something very similar to what I'm doing now in the other section class. Similar, but there's just nuance differences. And sometimes I'm clearer on one point and sometimes less clear on another point. So, you might benefit from also watching the video from the other class if you just really want to make sure that you're hearing all the details on this exam. But all right, but we'll get to that. All right. So then I'll tell you right now, the answer to 3, it had better be radians squared per second squared. That 625 is in radians squared per second squared, no matter what kind of function this is, whether it's measuring temperature or linear position or angular, whatever D is measuring, doesn't matter. That constant had better be in radians squared per second squared. If you're following everything I'm saying, that follows. So I just told you the answer directly to number 3. That probably means that on your exam, I'll ask a question similar to that, but not the exact same question, right? I mean, maybe I'll ask what units standard frequencies in or something, but anyway, but maybe I won't. Number four, I'll say the whole point of all of this is we're trying to show that anything that has the fundamental mathematics of a mass on a spring will act in every way like a mass on a spring. That's why we're spending so much time on a mass on a spring. We're ultimately saying it covers all of these systems in the world, whether they're pendulums on strings or temperature variations or subatomic particles like in PChem. This is all meant as prep for PChem, honestly, in some big way, and the Schrodinger's equation and stuff like that. But so what this question is like taking us seriously on that, it's saying, all right, so this means if we believe all this math, we're believing that the temperature is going up and down as though it were like attached to a big spring, sending it up and down. Now, there's no literal spring in the clouds, but we're saying this is as though it's on a spring. And if we give you the mass, which we do here, then you could figure out how effectively, metaphorically stiff, how figuratively stiff that figurative spring is. You're being asked to solve for the K of this supposed analogy spring. The way to do that, to cut to the chase, is what you need to understand for this question for number 4 is that omega equals the square root of K over M. It does. But let me warn you again, that is not, in my mind, that is not a GDP. I mean, in itself is not a GDP. That omega equals the square root of K over M. It's true. And you're totally going to use it for this problem. But you want to show me why it's true. You want to do that thing that we definitely did in class on some video recently. You want to do that thing of writing out, of writing out the differential equation for a spring. The differential equation is all came from originally was d2x dt squared equals negative K over M x, right? It all originally came from Hooke's law being applied to Newton's second law, right? So you walk me through that here. Walk me through in your GDP that d2x over dt squared equals negative K over mx, and then say, try the solution, x equals x naught cosine omega t. Take 2 derivatives of it. Show that the second derivative does get you back x, kind of like you did it in step 1, right? I mean, in part 1, take 2 derivatives of it, but then show like, aha, yes, this cosine omega t solution works as long as omega is the square root of K over M. You're showing me the same, right? You apply the logic from number 1 to K over M. So or however you want to do it, but show me why you believe that omega equals the square root of K over M. But once you establish that, then, square both sides. So you say, and then multiply both sides by M. So you'll have K equals omega squared times M. And that's how you solve for the K for that. Okay. Again, I'm just walking you through, like you'll work this out with your friends and I hope you do. Okay. Last thing about this, I'm looking at the time. true or false. When it says, so this is just like homework number 2, right? Like the math methods homework. When it says true or false is one possible solution to the differential equation as well as the condition. The condition it means, someone asked me this in chat a lot, or somewhere, someone asked me this. The condition it means is the condition that D naught equals 150K, like the initial condition, the initial value of the temperature. So it's saying if you assume that, and you assume the differential equation, are these solutions. And I will tell you right now, the answer to these particular ones is true and then false. Use that as a test yourself. Like when you go home and study or look at this, see if you believe me or see if you understand why. Now you have to show why, but I'm telling you the first one is true and the second one is false. And if you just write that, that's not good enough because I just told you. Okay, but if you understand it, then you know you're in good shape. So that's problem 1. Again, you could stop. I know I'm sounding intense. I'm just sounding intense because I'm trying to get you all this information. And again, just please understand, my goal is for you to do well. My goal is for you to understand this. It's not to find out if you understand, it's to get you to understand it. So I apologize for the intensity, but you still can't stop me anytime in chat. Please do stop me or slow me down or whatever. Okay, problem 2 is math, very much like homework number 2, right? Very much like homework number 2. But you notice, just like typical physics or typical exam, like you're given this differential equation again. And if you're still tentative in your understanding, if this is still like new to you, you might look in that parenthesis, or if you like the way I was in college, like I would see a thing like that, not always, but often. If I looked at a thing like that differential equation, and I looked and I saw in the parentheses a K and a Q and an R cubed, I would be bugging. I mean, I don't think we had that word then, but I would be like, wait, what? What R cubed? Just like, by the way, if I saw that first problem, I'd be like, temperature. When did we ever talk about temperature? What is temp? Are you crazy? And I would start panicking and getting pissed at the professor and like hating everybody. I don't want you to hate everybody, and I don't want you to hate yourself. I want you to understand the reason that temperature all of a sudden came up in the last question, and the reason KQ over R cubed is suddenly coming up here is we're trying to show you that what you've learned is a general principle that applies to all seemingly new situations. We're really trying to show you that the seemingly new situations are not new. Again, what that means is assume if you see something that seems new or weird to you, give yourself and me and the universe the benefit of the doubt and assume that it's not actually some new wild thing that's unfair and out of nowhere, that it's just another example of something you do know. What am I getting at? I'm getting at here where it says KQ over R cubed. That all looks very complicated, but K, it tells you, is a constant. Q is a constant. R is a constant. A constant cubed is still a constant, and a constant times a constant divided by a constant cubed is a constant. So that whole parentheses is just a constant. We're trying to get you used to the idea of the format or the form of this differential equation. You're going to see it again in PChem, and it's going to look totally different. But if you really get this, you'll see that it's totally the same. Okay, so that whole thing in the parentheses is a constant. So that whole thing in the parentheses, in effect, is omega squared. Right? It's just like, it's really very much like the last problem, just looks different. So it asks you in number I, so now I'm just like talking. I'm like, you could do, again, make a graph. I mean, make a diagram of some kind here. Probably it will be a cosine graph again. Maybe you'll come up with some other idea that's even better, but don't forget to make a diagram and make clear what the question is. But now the question here is show why or how the following expression is or is not a solution. So the way to do that is just like homework 2. You want to take 2 derivatives of it and see if what you get back is the original x times KQ over R cubed times a negative sign. That's what you're trying to show. Now, if you've been following stuff in class, and if you like, you might see that pi squared over 9 and be like, what? Pi squared over 9? If you've been following class lately, you'll realize that pi squared over 9 is just an additive term. It's a phase constant. It's a phi. It's allowed to be there now. And if you carefully, so you might, some of you who are listening to me right now, some of you might even look at that expression and with your eyeball at this point, some of you are in command of this enough to look at that thing and with your head go, yeah, that works. And by the way, you're right. It does work. That one, x equals x naught cosine bracket, that whole thing under in the middle of the page, like this whole thing, it does work. The answer is yes, it does satisfy. Now, maybe I'll change it slightly, or maybe I won't before the exam, but the answer to that is yes, it does work, but it's not good enough to just say, yes, it does work. You have to show me. So how do you show me? You take two derivatives of it. And when you take two and explain it out with the chain rule, blah, blah, blah. Once you do one thing once in this exam, if you ever have to use the same explanation again, you can refer me back. You don't have to keep doing the exact same explanation every time. But the explanation here involves the chain rule and the cosine derivative. And show me that even when you take two derivatives, that pi squared over 9 doesn't mess things up. It will still be fine and work. It is a solution. Okay, you could even maybe, if you really get this, you could say that thing is a phase constant. This is what we mean by phase constant. Anything you really get in this exam, go to town and show me that you really get it. I'm going to waste, no, I'm not going to wait. I'm going to take another minute and remind you. Will I? One way of also knowing where to show me stuff and where to go to town and how much detail to provide is any place at all. And this is such an important exercise. As you're going through this, whether it's through a rough draft or the final draft, and you really should do at least one rough draft, like hand in something to me that's really neat and checked and all of that, please. Like hand me something that you can take pride in. That's a final presentation. And that's easy for me to grade. When you're going through and you're trying to decide how much to write or what to say to show that you really understand it, one good litmus test is always, as you're going through, try to remember a time when you didn't understand this stuff. It might have been a day ago. It might have been 3 weeks ago. But remember your mindset when you didn't understand one of these things, okay? And realize that you do understand it now. And the thing to explain is how you got from there to here. Like almost acting here like you're teaching it to me. That will, if you can show, in other words, like with omega squared, like maybe you didn't understand chain rule before, but now you do. So therefore, that's a thing to spell out. The problem in physics is that, well, I'm not going to go. Anyway, do that. Okay, so now the next one, show why the following expression. Okay, so now this one looks like, whoa, where's this coming from? I mean, it was all over homework 2, but I know we didn't go over this part of homework 2 ever yet. And that's fine. I'm going to tell you right now what the deal is with it. There's 2 deals with this. Deal number 1 is you still need the chain rule. You're still going to do the chain rule. Deal number 2, in the GDP, in step 3 GDP, I highly recommend that you write down something like this. If y equals e to the x, now I'm saying y and x, right? I'm going general now. Like there's no y in this question, but I'm going step 3, GDP in general. If y equals e to the x, then dy dx equals e to the x, right? I'm reminding you, and you remind me in here that the derivative of the exponential function, e to the x, is itself e to the x. That's like actually the point and the inner content of the exponential function. The derivative of e to the x is e to the x. Now, how do you do like the derivative of e to the 2x or something? You use chain rule. You say the derivative of e to the 2x is e to the 2x times 2, okay? So that's what you're going to do here. The only other issue is what's going on with that lowercase I there. That I is indeed the imaginary number I. What? Where's that? Where's that coming from? Here's the deal. It's just a number. It says on the top, I is a number. It's a constant. It's an interesting number, just like pi is an interesting number, but it's just a constant number. It happens to be the square root of -1. That's what I is. So treat it that way when you take derivatives. It's just a constant. One thing to notice about I is that when you square it, since it's defined to be the square root of -1, when you square it, when you square it, you get -1. Okay, just bear that in mind. In fact, and like you might even say, but why are we even dealing? Why is I coming up? I'll tell you why I is coming up. Well, you'll see when you practice or if you did homework too. So I'm not going to tell you the answer to this one. You'll figure out whether it works or not. But you have all the knowledge you need to figure it out. And why I is coming up, just a quick fact I'll say, if you follow it, good. If you don't, think about it. But I to the first power is the square root of -1. I to the second power is I squared, -1, right? Okay. I to the third power, you may remember this from like 7th grade or something, or whatever, 10th grade. I to the third is I to the first times I to the second, right? So it's I times -1. It's, in other words, -1 times I. It's -I. I to the third is -I. You don't have to memorize that. Just follow the logic of what I'm saying. I to the first is by definition. I to the second you can do by squaring I to the first. I to the third is I to the first times I to the second. That's -I. I to the fourth is I squared times I squared. Right? I to the fourth is I to the second times I to the second. What is that? That's -1 times -1. That's 1. I to the fifth, I'm going to stop now. I'm not just making nonsense to you, but I to the fifth is I to the first times I to the fourth. That's 1 times I. In other words, I. What is my point? My point is, that I cycles in groups of 4. If you take 4 powers of I, you get back to I. Take 4, it cycles back to I every 4 steps. Just like cosine, you take the derivative of cosine, you get negative sine. You take the derivative of negative sine, you get negative cosine. You take the derivative of negative cosine, you get sine. Take the derivative of sine, you get back to cosine. They're related in that way. So that's why I is being used here, to see if that helps or hurts the differential equation. You'll find out, but you have all that you need. And same thing. So one of these terms has an I in it and one doesn't. And you'll see what difference I makes with the negative signs and all that. All right, that's that one. Now, we have 9 minutes left. I'm going to tell you right now, this next problem, hook on a hook. First of all, it says number 2. It says error. It should say number 3. This is really the third problem of the test, okay? This is the third problem of the test. And this one is long. It's involved, and it's based on what you did in your lab number 2 back in the day, but it's also another example. It looks crazy, but it's another example of the same thing. It's saying, as long as we know this differential equation, whether it's applying to temperature or to X position or to theta angular position, if the differential equation applies, then the system is an oscillator, a harmonic oscillator. It's a totally different situation that's trying to show you it's the same situation, okay? So it's involved, this problem. It is involved, but you've done a lot of the work in lab 2. But here's my real point to you, and I hope this is clear. I'll check in a second if it's clear. This problem, I walk through in detail, like excruciating detail. I walk through this problem for 2.5 hours in a video that I made in the Tuesday morning class. That's been posted. You may have already seen in your Google Classroom. It's like video 15 or 16 or something. It says like midterm prep walkthrough pendulum problem. That's this. Okay. Like I talk about it for 2.5 hours, just this problem. So please consult that video if whatever you want to know about this problem, but I'm not going to do it twice. Okay. And of course you could text and email me questions after you watch that video or scroll through that video, but that's all on a video in your Google Classroom. So that brings us finally to problem 4. Okay. So again, right. I mean, your exam might be all of these problems. You might not have a choice, but you might have a choice. But hopefully I'm giving you a big basis to work with for each one of these. Now, problem 4 is entirely, I'm going to switch screens in a second for the next 7 minutes. Problem 4 is asking you now really to show your words and your comprehension for something that looks much more free form here, right? This is much more open-ended, but there is a right idea here. There's a right answer, but it could be expressed all kinds of different ways. This is a little bit more like an essay. Now, where are you going to get the information that I'm looking for this right answer for number 4? Well, first of all, this is really what lab 3 and lab 4 are really all about. Okay, the last problem was lab 2. The other problems were lab 1. this is really, lab 3 and lab 4 are meant to show you the answer to this. But even more specifically, I'm going to switch screens now. More specifically, for 6 minutes. Hold on, sorry. Right. More specifically, well, this whole business, this whole class that was 2 days ago, Monday of this week, the video for that class, once I finally get rolling, which always takes me forever, once I finally get rolling and getting into the meat of all this, that is the explanation I'm looking for problem 4. Problem 4 is really asking you, do you really understand what we learned 2 days ago? Now I'm going to try to briefly review it again right now. There's still much more I could say about it. I will say more about it in next Monday's class. So you can also use that video. Like, hopefully that will also help you for this question 4. I mean, honestly, like, it will, but you could in principle do this question 4 now if you follow what I was saying 2 days ago. And what I was saying was this, with 5 minutes left. What I was saying is, if you take a bunch of identical vertical oscillators. Wait, I'm going to switch the screen for this last bit. Sorry. Okay, if you take a bunch of identical vertical oscillators and you distribute them equally spaced along a horizontal axis, for example, so you have a bunch of oscillators that are like, the first oscillator is at the 0 at the edge of a meter stick, and the next oscillator is like at the 1 centimeter mark, and the next oscillator is at the second 2 centimeter mark, et cetera, et cetera. And each one of these oscillators can go up and down with the same angular frequency and the same amplitude, right? So you have all these identical oscillators all spread out in a horizontal axis, but each one of them is going to oscillate vertically. If you do this one clever thing of staggering their phases by a constant step, a constant amount, then we get this fabulous phenomenon. When I say staggering by a constant step, I mean K. K, right? Like each one of these oscillators goes up and down at an omega t rate. Sorry, each one of these oscillators goes up and down in time at a rate of omega, right? But each one of them can start at a different phase, phi, a different place in its cycle. If, for example, the very 0th oscillator, the oscillator at the 0 position on the meter stick, the edge of the meter stick, that one, let's say we plug in 0 for x. So its equation would be y equals a cosine omega t plus 0. It has no phase constant. It starts right at the lowest amplitude position, right when our stopwatch starts, right? But then we go to the next, we look at the next oscillator, which is at the 1 centimeter mark. So we plug in 1 for x. Say we deliberately make this oscillator have a phase constant of pi over 2, like i.e. a quarter cycle out of phase with the first one. So that would mean that this one is like at the equilibrium position while this one is at the lowest amplitude position, right? If this one has a phase constant of pi over 2, it's starting a quarter cycle ahead of the other one. But then the next one, let's say it's at the 2 meter mark, so we plug in 2 for x. So we would say that its phase is 2 times pi over 2. So its phase is pi. That means that it's a quarter cycle ahead of the guy next to him, but it's 2 quarters of a cycle, 1/2 cycle ahead of the guy all the way in the edge. In other words, K, right? So K in the example that I'm making right now, in the example I'm saying, K would be pi over 2 radians per meter. K is the number of radians that you add in phase for each meter that you walk across this arrangement. So omega is measuring the rate at which each oscillator goes up and down in time. K is measuring the rate at which we do cycles per unit space, right? And what happens when we put these two things together is we see a wave. We've never seen a wave before. One key thing I'm trying to say here is oscillator is not a wave. But a bunch of oscillators put together in this fashion, a bunch of oscillators put together with their phases staggered by a certain amount, that's a wave. And what I mean by a wave is what you did in lab 3. Like you stand on one end of the string and the other person stands on the other end, and you flick the string and you see this bump or this hump or this crest or this trough travel from, and I know we have 1 minute, just let me finish this point and then we're done. But what by wave, I mean the idea that you send this disturbance, this distortion of the metal string from you to your lab partner. And this disturbance travels a certain amount of space in a certain amount of time and can have a velocity that's calculable. And in other words, it's a motion that is subject to every scientific standard I know. But all that's moving is pieces of metal, and no piece of metal actually moves horizontally from you to your lab partner. That's the essence of a wave. It is unthingy. It's the first unthingy thing of this class. A wave is an immaterial motion, right? Like lots of metal are doing lots of little motions, but no metal is actually moving horizontally across the horizontal axis. Yet something is. It's not a thing, but it is something. It's a distortion in the shape of the metal. A bump moves across. That's called a wave pulse. How do we make a wave pulse? This way. We make cosinusoidal oscillations in time and in space at the same time. That's what you're trying. So I will explain more about that next Monday, but I explained it last Monday. That's what I'm looking for, is an explanation with pictures, with as much detail as possible, with math equations. Show me how you put a bunch of oscillations together to make a wave. That's question 4. So I have to go to a different class now, so I can't answer questions right now, really, but hopefully this is all clear enough. Text or email me if it's not. You've been wonderful as usual. I'm going to, so thank you. So I'm done.
Have a good day, Professor.
Bye. Thank you.
Bye. Thank you. Thank you. Oh, cool. Oh, great. Oh, thank you, Katya. That's a great thing to say. Thank you. That's cool. Yes, great. Okay. Okay, cool. And you're good, Rashwan? Makes sense?